Welcome to this video on more challenging trigonometry problems. Okay, so here we've got three questions which require a little bit more than just simply solving a right-angled triangle. So let's look at this first one here. We've got a diagram of a triangle ABC, and we're given these dimensions, okay, which are on the diagram already. And we've got to calculate the length of the perpendicular from A to BC. So what is that? Well, let's draw it in. So the perpendicular that drops down from A to the baseline BC is that line there. Okay, and because it's perpendicular, it makes a right angle at the bottom. And we've got to find the length of that line, X, I'm going to call it. Okay, now we can use trigonometry, and what I'm going to do to simplify the problem a little bit is to extract the left-hand triangle from that diagram and recreate it over here a little bit bigger. So that's our line that's joining B and A together. We've got a vertical line down there, and we've got a line joining those together there with our right angle in the corner. Okay, there is our height X that we've got to find. We know that this is 6, and we know that this is the point A and this is the point B. Okay, and we do have an angle here, okay, which is 52 degrees. Okay, so all that information is provided for us, and I've just extracted it there and recreated it. So we have a right angled triangle now that we can use, and we know that in a right angled triangle, if we've got an angle there of 52, X is opposite and 6 is the hypotenuse, and O over H is the sine ratio. So we know that for question A we know that the opposite over the hypotenuse is equal to the sine of 52 degrees. Okay, and we have an equation to solve in X. If we multiply both sides by 6, we get that X is 6 times the sine of 52. Making sure the calculator is in degrees, if we put that into the calculator, that gives us 4.728 to 4 significant figures, and then it goes on after that. And what we're going to do is we're going to use 3 significant figure rounding, because that's normal in this kind of question unless you're told otherwise. So my answer that I would finally give would be 4.73 centimeters to 3 significant figures. Okay, and just look at the diagram, roughly drawn to scale. It seems about right. Okay, you obviously wouldn't expect it to be larger than 6, for example. So that's that. Now, if we took question B, we've got to do the area of the triangle. That's the area of the original triangle. Well, the area of a triangle is half base times height. Okay, and the base is 9. So it's a half of 9 times the height. And the height we've just worked out to be 4.73, but I'm going to use at least one significant figure more than that, because when we want an accurate answer, we must work to more degrees of accuracy than the final answer. So that will be sufficient, and if you put that into the calculator and round that to 3 significant figures, it gives you 21.3 centimeters squared, because it's an area, to 3 SF. Okay, so they're the 2 answers required for that question, including the very important and necessary working out that you must show. Okay, next question. And this one concerns a circle. No right angled triangles visible anywhere, but that's what we're going to work on. So we're told some information. SR is a diameter. That means it's going right through the middle of the circle, 25 centimeters long. PQ is a chord. That's a line that cuts from one side of a circle to another. It's cutting the diameter at 90 degrees. Various information there to support it. Now it's telling me that the length XR is 1 centimeter. All right. Now, when you look at that in proportion to OR, which is 25, it does rather look as if it's too large and that this line PQ should be a lot closer to the edge. So what I've done to make things a bit simpler is recreated the diagram a bit more to scale. Okay, so this little bit that's supposed to be 1 is now just this little bit here, and that means the rest of this line from O to R is 24. Okay, because I've taken away that 1. This is still 25 because it's a radius of the circle, OP. All right, now what I'm actually trying to work out ultimately is the length of the arc PQ. Now the arc is the curved part of the circle between P and Q. Okay, so it's the length of that yellow piece of line that I've drawn there. Now before I can do that, I need to know the angle that's in the middle here, okay, which I can then double to find the total angle in the middle from there to Q, from P to Q. Okay, so whatever angle this is in yellow, I double it, and that will give me the angle between P and Q, which will tell me what fraction of a circle this yellow arc is. Okay, so it's quite a complicated problem. I'm going to call this angle in here alpha. Okay, and I'm now going to recognize that using trigonometry, here's a right angle triangle, that the cosine of alpha, the cos of alpha, is the adjacent over the hypotenuse, right? 24 over 25. And if I put on the calculator the inverse cosine of 24 over 25, okay, that will give me the angle. And to 4 significant figures, that comes to 16.26 degrees. Okay, 16.26. So that is the angle alpha. So 2 alpha, which is the total with that plus that bit there as well. So 2 alpha is going to be double that, which is 32.52 degrees. Okay, so I now know that this piece that's been cut away from the circle represents a fraction of the whole circle, and the fraction is 32.52 over 360. Okay, now the circumference of the whole circle is 360 degrees. So I need to work out 32.52 over 360 of the circumference of a circle. And you should know that the circumference of a circle is 2 pi, that's a times there, 2 times pi times the radius, which is 25. Now if you put that onto the calculator, so that division, multiply it by 2 times pi times 25, that gives you 14 7.2 centimeters to 3 significant figures. Okay, so quite a complicated problem with several stages involving trigonometry, but also involving circles and the arc length of a circle when you're given a fraction of the total of 360 degrees. Okay, so that's how I would answer that problem. You don't have to draw this extra diagram, but it just helps to put things in perspective. A third question here. Now in this question we have a semicircle and a triangle. Okay, we're told certain information about it. We're told that the circle has a radius of 5, which means the line AC must be 10. Okay, and we're told also that the length of BC is 7. So that's there. But we've got to calculate the length AB, which I'm going to call X. Now we don't have any angles on the diagram, but we do know one of them. And this goes back to one of the circle theorems. The angle in a semicircle is 90 degrees. So where that angle is made going from one end of a diameter to another, that angle is 90 degrees in there. So we can now tip that over and we can see that we have a right angled triangle. If I redraw it over here, something like this, okay? So I flipped it over. We've got a height of X. We've got a base of 7. Okay, that's 7. That's our right angle. That's 10. And this is X. We can now see that we don't even need to use Pythagoras trigonometry. We can use Pythagoras theorem. Okay, because if we know a short side and the hypotenuse, the long side, we do that x squared is 10 squared minus 7 squared. Okay, and that's 10 squared minus 49, which is 51, which means that x must be the square root of 51. Now, if you put that in the calculator, that comes to, usually we would give this to 3 significant figures, and that would give me 7.1423 significant figures, and it's a length, it's centimeters, so 7.14 centimeters to 3 significant figures. Okay, and that's the answer to that question. So these are 3 examples of questions involving trigonometry, or at least right-angled triangles, where it's not immediately obvious where to start, and the final answer might require other areas of mathematics apart from trigonometry and Pythagoras. Okay, so I hope that was helpful. Take care.